do. So, good morning, everybody. Welcome to another exciting morning, the last morning this semester of Chem 1211 with me, your host, Dr. White. Thank you very much for being in my course. Oh, we got some more people showing up, but thank you very much for being in the course. Don't forget, Monday is the final. It will start at 10 a.m. when I send out the email for it. You have until the whatever time, 2 or so, to get it uploaded. All right, let's get going. All right, can everybody see chapter 11 on your? Thank you. And this is the last day you'll have to thumbs up for Dr. White. All right, when we talk about gases, you should know that gas pressure is measured in the following units: milliliters, millimeters of mercury, and torr. And as per the important information, the final exam, 760 torr equals 760 millimeters of mercury equals 1 atmosphere. So if we look at number 3, and this was on test number 3, how many atmospheres is 741 torr? We're trying to find atmospheres. We're given torr. We use our good buddy, our good friend, unit analysis. This is what we're going to start with. This is what we're going to end up. How do you do that? Whatever you're trying to get to goes on top of a ratio. Whatever you're trying to get rid of goes underneath. Where do you get this? Note 760 torr equals 760 millimeters mercury equal 1 atmosphere. Remember, 1 atmosphere and 760 are both exact numbers. So this is 3 significant. My answer is 3. And notice, and I did it on test 2, number 4, how many torr is 1.237 atmospheres? Trying to find torr. We're given atmospheres. We have atmospheres. We're going to torr. Torr goes on top using unit analysis. Your good buddy, your good friend. Atmospheres goes underneath. These are exact number, 4 significant figure. My answer is 4 significant figure. Now, the next thing I taught you was Boyle's law. Now, let me open up something that I should have opened up, but I didn't, but I will now. Everybody see on their screen, important, thank you. And if we scroll down, you'll see Boyle's law. And this will be given. P1 times V1 equals P2 times V2, where P1 is the initial pressure, V1 is initial volume, P2 is final pressure, V2 final volume. And if we go back to our question, if a balloon has a pressure of 658 torr and a volume of 1.894 liters, remember liters is volume, what is the pressure of the balloon if the volume is increased to 5.133 liters? And what are we being asked to find? P2, the final pressure. In other words, the pressure after you make a change from the initial pressure. And we're given the initial pressure here and the initial volume, and the volume is increased, which means that's the final volume. So we're trying to solve P1 times V1 equals P2 times V2 for P2. We want to get P2 alone on one side. How do we do that? We divide by V2 on this side, because anything divided by itself is the number one and cancels out. But whatever you do on one side, you have to do the other. And when this cancels out, you get P2 equals V1 times P1 divided by V2. I like to rewrite it. You don't have to. Put the numbers in, and you get your final answer. And I gave you a couple of practice, and you should practice these. Now, next, let's look at number 9. What is the weight of 5.77 liters of oxygen gas, O2, at 100 degrees C and 678 torr? Now, if you look at this problem, are we changing any of the variables? No, we're dealing with a gas. Therefore, if you're not changing the variables and you're asked to calculate something and you have a gas, and for those of you here, if it's 15 points, I didn't say that, it's the ideal gas law. And under important information, I have the ideal gas law, PV equal nRT. Now, it's important to know, and this is a common mistake students make on using PV equal nRT. Pressure has to be in atmospheres. Volume, V, has to be in liters. I'll always give it to you in liters. And N is the number of moles. No, I'm not going to give you moles. You get grams if I'm going to give you a weight. T is the temperature in Kelvin, and R is the universal gas law constant, 0.0821 atmospheres, liters, mole K. And this is 3 significant figures. Now, up here in important information, I give you the conversion, how to go from centigrade to Kelvin, Celsius to Kelvin. So let's go look at our problem. Now notice we're asked what the weight, but wait, PV equal nRT doesn't have a weight, but it does have N moles. So therefore you need 2 steps. In order to find the weight of the oxygen, you first have to find the moles of oxygen and then convert moles to grams, which you learned for test number 2. So what are we first doing? Solving for N, moles. We're given trying to find the grams, we're given the volume, temperature, pressure, and in important information, you're given R, the universal gas law constant. So how do we solve for N? Get it alone on one side. Well, it's times RT. If I divide by RT, that anything divided by itself, number 1 is gone, I get N alone. But whatever I do to one side, I have to do to the other. And now I have N equals PV over RT. I'll rewrite it. Now, as I said before, we have to find pressure. We're given volume in liters, so you don't have to change that. We're given R and temperature, but these are in the wrong units. Temperature has to be in Kelvin. So over here, to convert temperature to Kelvin, degrees C plus 273, degrees C for this problem is 101, plus 273 is degrees, temperature in Kelvin is 374 Kelvin. Now, pressure for PV equal nRT has to be in atmospheres. Oh no, he didn't give it to us, and I won't, in atmospheres, because I've never seen a gauge, and there aren't any that I know of, that measure in atmospheres. What they do measure in is either millimeters of mercury or torr, and we have to convert torr to atmosphere. Use your good buddy, your good friend, unit analysis. Atmospheres goes on top, torr goes underneath. Where do I get those numbers? Well, in case you forgot, you look at important information. 760 torr equals 1 atmosphere, ATM. So I can put 1 atmosphere, 760. These are exact numbers, three significant figures. So now we have pressure in atmospheres, volume was in liters, R is in the right units, and temperature, which we have over here, is in Kelvin. And this is the moles of oxygen. Now, are we done? No, you have to get the grams of oxygen. And now we need step number 2. How do we do that? Here we have moles of oxygen. We're trying to get the grams of oxygen. And probably one of the last times this semester I can do, it's time to use your good buddy, your good friend, unit analysis. Threw in an extra one. Yay. And it has been my good buddy, and hopefully it has been your good buddy this semester. Whatever we're trying to get to goes on top. Well, first of all, the answer, what units do we want? Grams of oxygen. That goes on top of a ratio. What are we trying to get rid of? Moles of oxygen. That goes underneath. Where do we get these numbers? Well, in case you forgot, one mole of a compound equals the molecular weight of that compound in grams. And on the next page, the molecular weight of that compound is the sum of all atomic weights. So what's the atomic weight of oxygen? Because 1 mole equals, molecular weight of oxygen gas. And that's the sum of all atomic weights in that molecule. 2 oxygen to 3 significant figures. The atomic weight of oxygen is 16.0. There are 2 of them. That's 32.0. You go here, exact number, 3 significant figure, 3, and this is this. Now, there are 2 ways of doing significant figures when you have multiple calculations. One, round off at the very end, or round off at each step. I'm a round off at each step, but on the final, as I did on the test, I will calculate both ways and either one will be right. In this question, guess what? It was the same both ways. And another variation of this is number 10. And here, if you burp, 86.75 grams of CO2 at 545 millimeters of mercury at 34.6 degrees C, then what is the volume of your burp? Excuse me. And here we're trying to find volume. We're given a weight, we're given a pressure, we're given a temperature, and later on we'll need R, which are given, the universal gas law constant. Now notice here, and as we've written here, we're talking about a gas and nothing is changing. And when that happens, that tells you PV equal nRT is the formula you should use. We want to solve for volume. Since we're only solving for volume, which is already part of the expression, this only needs one major calculation. Solve for V, divide this side by P. Whatever you do to one side, you have to do to the other. I've done that. This cancels out. Now we have to convert pressure to atmospheres, which we just did using your good buddy, your good friend, unit analysis. Temperature, you have to convert to Kelvin. Here it is. We just did that. But here we're given grams. But N is moles. So we have to convert moles of CO2 to grams, or grams of CO2 to moles of CO2. And what we're trying to get to goes on top of the ratio, moles of CO2. What we're trying to get rid of goes underneath, grams of CO2. And where do we get this? 1 mole of a compound equals its molecular weight in grams. The molecular weight is the sum of all atomic weights. Carbon to 3 significant figures atomic weight is 12.0. There's one of them. 2 oxygen, 16.0 for atomic weight of each oxygen. Add it up, 44.0. Here's the moles. You put it in here, oops, and you get this number. And again, you can round off at the end, or like I do each step, and it turns out this gives it both ways. Now, what I don't have here, but you can go back and look at the test, is using Dalton's law of partial pressures. That's the sum, the total pressure is the sum of all partial pressures of a mixture of gases, and that mixture would be, the partial pressure is the gas pressure of the gas in the mixture as if it were alone. That's P total equal P1 plus P2, and we've done enough of those. Since more people are here, time for a commercial from Dr. White. Don't forget, do the student evaluations online, please. That would help me out. If you like what I did a lot, go to ratemyprofessor.com and tell people. And if you didn't like what I did this semester, go there and tell people. If you really, really, really like what I did this semester, or if you really, really didn't like what I like that, didn't like what I did this semester phase, hopefully you liked it, write a letter to the Board of Trustees, copy the president. You can find their email by going to my favorite search engine, Google. Have you noticed I'm old style, or I just don't use Google as a verb? But anyways, put in COD, Board of Trustees, you'll find their email like this. And same thing, COD president, and you'll find his email. And a commercial. I assume everybody can see chapter 15, practice problems, right? Yep, thank you. All right. And as you saw in test number 4, name one key factor of the collision theory of reactions in order for a chemical reaction to occur. Well, molecules must collide. You only have to put down one. And collisions must have enough energy to make a reaction, and they must have proper orientation. Now, on the test, I asked, how does an activation energy work? And it lowers the activation of the, how does a catalyst work? It lowers the activation energy, but what is the activation energy? That's the amount of energy needed in a collision to make a reaction occur. And here, let's talk about energy diagrams. This is an exothermic. When you have exothermic, the product or products are lower than the starting materials. Here's the activation, Y energy, X time. For an endothermic reaction, you have the products have more energy than the reactants, so they're higher. The activation energy is still from where you start to the top of the hill. Next, we talked about equilibrium constants, and this was one actually on the test. Remember, it's the power, the concentration of each product to the power of the coefficient times each product divided by the reactants on the bottom to the power of each reactant. And next, I asked you about predicting relative amounts of products and reactants. When K equilibrium is greater than 1, there are more products than reactants. When K equilibrium, this is 10 to the minus 34th, is less than 1, then the reactants are greater than the products. Then I talked about Le Chatelier's principle, which I just used my North Side Chicago French accent. And let me do one for you. And first of all, let me copy it down because I'm going to put this on my whiteboard. All right. And let me do one thing I forgot to do. All right, let's go through this. I assume everybody can see my whiteboard. For the following reaction, heat plus CO plus water in equilibrium with CO2 and hydrogen, what happens to the concentration of water and hydrogen when I add some CO2? And what happens to those concentrations of water and hydrogen when I put the reaction in boiling water? And it's your turn. On the last day of class this semester, I'm going to share some fun again. Have you noticed if I said fun enough times, you might believe me? And it's working. And another public service announcement, don't forget, hand in your lab that's due today. Make sure you upload it. I hit the wrong polling. Sorry about that. Let's do the right one. And it looks like everybody's done, so I better get to work. Now, at equilibrium, there was a certain amount of heat, CO, water, CO2, hydrogen. When I add more CO2, the equilibrium says, you know, equilibrium can talk, but they can. They say, oh no, we've got too much CO2. How do we get rid of it? The only way is CO2 reacts with hydrogen to make more water and more CO2. Because when something reacts, it's consumed. You have less, which means for hydrogen, it will be consumed and it will decrease. And since we're making more water and CO2 to get rid of the excess, or CO to get rid of the excess CO2, then you're making more carbon monoxide, CO, and the amount will increase. Now, if I put it in boiling water, what does boiling water do? Adds heat. Ice bath removes heat, boiling water adds heat. So let's clean this up and at equilibrium, there was a certain amount of heat, CO2, CO, water, CO2, hydrogen. Now we've added heat and says, oh no, I have too much heat. How do I get rid of heat? Heat reacts with CO and water to go that way to make more CO2 and hydrogen. Well, if heat is reacting with water, water is consumed. And if something is consumed, guess what? Just like my French silk pie, luckily I never went out and bought one. I need one like a hole in the head, but it will decrease. And since we're going this direction, can I make that any arrow any more sloppier? Yes, I can. But anyways, we're going in this direction and we're going to make more carbon dioxide, CO2, and more hydrogen. And if you make more of something, hydrogen, the amount you have will increase. And that's how you do it. Wrong one. Right one. Shh. There's going to be a Le Chatelier's problem on the final. Shh. By now you probably figured that out, but in case you didn't, shh, don't tell anybody. All right. And let's finally go to chapter 14, which is acids and bases, actually second to finally. And here we have, you should know, what is a Bronsted-Lowry acid? A proton donor. What is a Bronsted-Lowry base? A proton acceptor. And as I had on Test number 4, you should be able to identify key acids and bases by its chemical formula, HCl, hydrochloric acid, and NaOH, sodium hydroxide. Also, you should know by now, sodium chloride is a salt. I can say this, I forgot to say it when I went over the test 4 answer problems. This semester, everybody got C right. I've had semesters where people put down acid or base for sodium chloride. I wonder, where have you been all semester? Luckily, that didn't happen this semester. And H2SO4, sulfuric acid, ammonia base, NH3, NH3 ammonia a base, HNO3, nitric acid, and acid. Now, what I don't have on there, but you should know, because I had it on test number 4, and this is sodium bicarbonate. And it's a base. And remember, it's in baking powder. Next, talked about pH. How do you determine pH? pH is minus the log of the hydronium ion concentration. And you should know this pH scale. See where I have note on the right? You should know that. This is probably the most important thing I'll teach you this semester, because you can use this the rest of your life. pH goes from 0 to 14. At 7, you have neutral pH. That's when the hydronium is equal to the hydroxide ion concentration. When you're above 7, you're basic, hydroxide greater than hydronium. Below 7, acidic, hydronium greater than hydroxide. And if you have something at neutral pH and you add a base to it, the pH number will increase. When you have something at neutral pH and you add an acid to it, the pH will decrease, become more acidic. And here I'm asked, what's the pH if the hydronium ion concentration is 1.0 times 10 to the minus third, pH minus log hydronium ion concentration is 1.0 times 10 to the minus 3. When it's minus log of 1.0 times 10 to the minus x, then the pH is x, in this case 3, it's acidic. Now, here, number 7, I asked for the following. If a solution has a hydroxide ion concentration, OH minus, times 1.0 times 10 to the minus 3, what is the pH of the solution? And is it acidic, basic, or neutral? And here you need 2 steps. Step 1, solve for hydronium ion concentration, H3O+. How do you do that? In important information, let's find out if I'm lying to you. I have what's the pH. Oh, look, I even give you a remember. Am I nice or am I nice? You don't have to answer that. And I also give you the ionization constant. H3O times hydroxide equals 1, or actually 1.0 times 10 to the minus 14. And we're going to use that. And here we want to solve for hydronium, get rid of hydroxide, because we want hydronium alone, divide by hydroxide concentration. Whatever you do to one side, you need to do to the other. And I did. And now hydronium is equal to 1.0 times 10 to the minus 14 divided by hydroxide. Put that in, do the math. I get 1.0 times 10 to the minus 11. Am I done? No, I'm trying to find a pH, but now I have the hydronium, and therefore I can move us over here. And second step, solve for pH. pH minus the log of hydronium. That's minus the log of 1.0 times 10 to the minus 11th. Therefore, the pH is 11. That's above 7. It's basic. And remember, a buffer solution is a special solution that resists change in a change in pH when a small amount of acid or base is added. So if I ask what happens to the numerical value of pH of a beaker of buffer solution, if you add a few drops of dilute acid, it stays the same. If you add a few drops of dilute base, it stays the same. Now, as you did in the last two labs, if we look at number 12, if you have to add 1.35 times 10 to the third milliliters of a 1.53 capital M molar solution of sodium hydroxide to neutralize 1.87 times 10 squared milliliters of an HCl solution, what is the molarity of the HCl solution? When you're asked to find the molarity of a solution, immediately that's a titration. And if we go to important information, oh look, titrations. At neutralization, moles of acid equals moles of base. And for a monoprotic acid or base, which is all we'll use in this class, milliliters of acid times molarity of acid equal milliliters of base times molarity. And at that point, we can go back and say moles of acid equal moles of base. Here's milliliters of acid, milliliters of base, times milliliter of acid equals milliliters of base times molarity of base. We're trying to solve for molarity of acid. HCl is an acid, hydrochloric acid. Therefore, we want to get, and here I have the line should have been through milliliters, not molarity. You divide both sides by milliliters of acid. You get molarity of acid equals milliliters of base times molarity of base divided by milliliters. You put the numbers in, and lo and behold, it's 11.0 molar HCl. Let me open up something. That's weird. There we go. Nope. And did I go through the solution? No, I didn't. Let's go through real quick. Everybody see solutions problem set? Thank you. Kelly, what did you have on your thumb? Oh, Dr. White is great. You have a smile thing. Hold on. I got to show the whole class. Kelly, say something.
It's Fun Friday. So I put.
Oh, thank you. Do it once more for posterity. Say something.
Say something.
Thank you. Dr. White salutes you. Oh, you're the first one I've ever done a salute to in my class. You can write that down in your diary. Hopefully you didn't do that in indelible ink, but if you did, acetone will take it off, or ice rubbing alcohol. All right, let's continue on. Give an example, and this is in the solutions chapter, of a colloidal dispersion, latex paint, milk, blood. Give an example of a solution in your daily life. Tea, pop, sugar, and water. Here are examples. If a solution has 12 grams of KBr and 10 grams of water, what's the solvent? What's the solute? The solvent is the component of a solution present in the greatest amount, KBr, and the other component or components are solutes, in this case, water. Now, let's look at number 7. Everybody see number 7? Kelly, it's your chance. Thank you. And who said chemistry can't be fun? What does 4.56 times 10 to the third capital M NaCl bracket AQ close bracket mean? What is the solvent of the solution? Capital M, molarity, moles per liter, moles per 1,000 milliliters. And if we find important information, final exam, you'll see molarity, moles solute per 1,000 milliliters. And the AQ in bracket means aqueous, which means the solvent is water. Now, if we look at number 9, how many moles sodium fluoride are in 12.5 milliliters of a 0.254 molar NaF sodium fluoride solution? We're trying to find moles of sodium fluoride. We're given the milliliters and we're given the 0.254 capital M sodium fluoride. What does that mean? It means 0.254 capital M is molarity, moles of NaF sodium fluoride per 1,000 milliliters. We only have the 12.5 milliliters to start with. Tea break. And we're trying to get the moles of sodium fluoride. Use your good buddy, your good friend, urinalysis. Oh, yeah, let's do that again. Better. And whatever you're trying to get to goes on top. Well, Danny, you can always email me and we can have a Zoom meeting. And whatever we're trying to get to goes on top. Unit-wise, whatever we're trying to get rid of goes underneath. Milliliters, where do we get these numbers? From here, 0.254 moles of NaF per 1,000 milliliters. 1,000 is an exact number. 12.53, 0.2543. My answer is 3 significant figures. Now, in real world, how many grams of sodium chloride are needed to make 345 milliliters of a 6.789 capital M NaCl solution? And here we're trying to get grams of NaCl, sodium chloride. Don't forget to ask, please pass the NaCl the next time you're at a restaurant or with friends and you want the salt. Now you don't have to do that. But anyways, we're given grams, we're given milliliters of sodium chloride, and we're given this number 6.789 capital M NaCl. And what does that mean? 6.789 moles of sodium chloride per 1,000 milliliters. Now, there's no way you can go from milliliters to grams in one step. You can't. You need 2 steps. Well, what 2 steps? And if you go, does everybody see the 2 steps on there? Thank you. If you go to important information, final exam, molarity 2-step problem, milliliters to moles, step 1, moles to grams, step 2. I can do that, and I did. Step 1, milliliters to moles. I have these many milliliters. I have trying to get to moles. I use my good friend, my good buddy, unit analysis. Moles goes on top of sodium chloride in the ratio. Milliliters go underneath. Where do I get these numbers? I look over here and see the molarity really means moles per 1,000 milliliters. Put 6.8789 moles sodium chloride per 1,000 milliliters. Remember, 1,000 exact number, 3, 4, 3 significant figures. Am I done? No, I want to get the grams of sodium chloride. And now I need 2 steps. And that second step is moles to grams. I have moles of sodium chloride. I want to get the grams of sodium chloride. So one last time, especially for Danny, use your good buddy, your good friend, unit analysis. Oh, I'm getting dizzy, I'm out of breath. And a special guest appearance. You don't forget to use your good buddy, your good friend, unit analysis. Who said you couldn't be a wild and crazy guy in chemistry? You can, and I did. Thank you, everybody. And using my good buddy, grams goes on top, moles go underneath. Where do I get those numbers? 1 mole of a compound equals its molecular weight. The molecular weight of sodium chloride is the sum of atomic weights. And here we are, 3, exact number 3, and there's my final answer. And with that, I'm done. The first day of class, I said, my world of chemistry is your world of chemistry. You don't know about that, but you will. And now you know my world of chemistry is your world of chemistry, and you know all about it. And don't forget to ask people, please pass the NACL. And if you ever ask anybody else, ever ask you how to use your good buddy, your good friend, unit analysis, you know how to use the whistle. You got to get your own whistle. I don't supply those. And with that, it's been a true pleasure getting to know a lot of you. I wish I had a chance to know more of you other than the name on the screen, but I hope you enjoyed the semester. I had a good time, but if you haven't figured out, I love chemistry. And with that, final time this semester, Dr. White's going to sign off in a second from COD North, my office. But don't forget, 10 a.m., I'll be sending out the password for your version of the final. Sometime Sunday, I will upload it to the Blackboard. Also, a couple of things. Next week, no classes, but I will have office hours if you need anything. Monday, I'll check my email during the final in case you have any questions. And what I will do is I apologize. I got a little behind this week. I got swamped with a lot of stuff. By Sunday morning, I will have, assuming you've already uploaded or will, all your final lab grades in Blackboard. If I'm missing something, email me and we'll work it out. And also next week, by Sunday at the latest, I'm hoping by the end of the week, realistically, I will have all your scores, including your test total, your final points total, your percentage, and your grade in Blackboard. I'll also upload your grade to the school system where you can see it. That usually takes 24 hours after I upload it to the school system for you to see it, but you can see it instantly once I upload it in Blackboard. And you'll be able to find out how you did, which is a good thing. And Erica, sure you can. If you haven't figured it out, I give an extra 24 hours after the deadline for labs because things like that might happen, like what you just asked, Erica. But anyways, with that, I'm done. Thank you for being in my class for a final time. Gang gesund, be healthy, wear your mask if you haven't gotten your vaccinations. I have, but I'm still going to wear my mask when I go to the supermarket because you don't know if other people are not vaccinated. With that, gang gesund, goodbye. Have a nice semester break. Bye.